Hello guys, Fromage here. Today we will be solving the same integral as the previous video, but by another method. So, let's get to it. The integral is integral from 0 to infinite of e to the minus x squared over 1 plus x squared dx. So, this term in the denominator is inviting the following variable change. We will say x equal tangent of theta. So the differential is dx equals secant square of theta d theta. And the integration limits are when x equals 0, then theta also equals 0 because tangent of theta is 0 for 0. And when x goes to infinite, then theta must be pi over 2. Yeah? So, now we write the integral. I will write I integral. No, not me. I equals, I get confused, integral from 0 to pi over 2 of e to the minus tangent square of theta over 1 plus tangent square of theta secant square of theta d theta. Yeah? Now 1 plus tangent square of theta is the same as secant square of theta. So we simplify and we get integral from 0 to pi over 2 e to the minus tangent square of theta d theta. So this looks simple, but it's almost as difficult as the original integral. So now we will arrange things a little bit. So this is the same as integral from 0 to pi over 2 of e to the minus tangent square of theta minus 1 plus 1 d theta. Yeah? So I keep here, I just subtracted and added 1 in the exponential. So I just added 0. Then we will take out this number from the integral, the exponential of 1. So we have I equals e times integral from 0 to pi over 2 of e to the minus, and then we got here minus tangent square of theta minus 1, that is minus secant square of theta. Minus secant square of theta d theta. Yeah. So now we will make a trick. And the trick is called Feynman trick. It's very useful. So we will introduce a parameter, so our integral will now be a function of this parameter a. We will rewrite the same integral and we will put the parameter in the exponent of the exponential. Yeah, d theta. Then you can notice that if we take the derivative with respect to a, we will get the secant square of theta out of the exponential. Yeah, that's the trick. Feynman trick. First, we'll just remember that we will recover our original integral if we put a equals 1. Yeah? So we have that I equals I of 1. Another thing that will be useful is that if we put a 0 here in this integral for a, then we got e to the 0, that is 1. So we have just the integral from 0 to pi over 2 times e. So, and this is, we can easily see that is e pi over 2. Yeah. So, now we will take the derivative. So, the trick is that we will get a differential equation for the integral on the parameter a. So, and then solve this differential equation. That will be easier than solving the original integral. Yeah. So here we will get, when we take the derivative, we got the minus sign from the exponential, minus e to the minus a secant square of theta, secant square of theta d theta. Yeah. Again, this the secant square of theta, we can rewrite it as tangent of square of theta plus 1. So minus e integral from 0 to pi over 2 of e to the minus a tangent square of theta plus 1. Yeah. Secant square of theta d theta. Yeah. So we will take out the constant term here that doesn't depend on theta. So this is I prime. Sorry. Minus e. So we have this 1 here is multiplied by minus a. So minus e to the 1 minus a integral from 0 to pi over 2 of e to the minus a tangent square of theta the square of theta secant square of theta d theta. Yeah, you seeing it now? Yeah, because now we have our original x variable here and the differential of x here. So we can reverse the original change of variable. The integration limits will be reverted the same as before, and we got I prime of a equals minus e to the 1 minus a, yeah, integral from 0 to infinite of e to the minus a x square dx. Yeah, nice. Yeah, I'll get another paper. Wait a second. Yes, just wait, my assistant. Yeah. So here is coming. Yeah. So then we'll rewrite the original I prime of a equals minus e to the 1 minus a integral from 0 to infinite of e to the minus a x square dx. Yeah. So this integral here is just the famous Gaussian integral, half of it. Yeah. So the result is minus e to the 1 minus a, and here is the result of the Gaussian integral is 1/2 square root of pi over the factor that goes in the exponent a. Yeah. So here is our differential equation. Is I prime of a equals this function here. So now we will integrate I prime of a between 0 and 1 equals, we will take the constant terms that don't depend on a, so minus e square root of pi over 2 times the integral of the function 0 to 1 of e to the minus a over square root of a dA. Yeah, now we are much better, we're in a much better position, because we know that this integral here, it will be just the I evaluated in 1 and 0, and we know already what is that, and this integral here seems like we can solve it easily. So, and indeed, we will make the variable change a equals v squared. So dA equals 2v dv. And we can easily see also that when a equals 0, v equals 0. And when r equals 1, v equals 1, because it's just a quadratic function. So here the integral of the derivative is just the function that is was derivated. So this is integral, is the I of 1 minus I of 0 equals minus e square root of pi over 2 times the integral, same integration limits, e to the minus v square, the differential is 2v dv over square root of a. When we take square root of a, we get v. Yeah? And now we can simplify the v's and the 2's. Then we got I of 1 equals I of 0 minus e square root of pi integral from 0 to 1 of e to the minus b squared dv. Yeah? Then we will replace I of 1 equals I of 0 that we already calculated, I pi over 2 minus, we will take out a factor here, I pi over 2, and then we introduce the same factor, 2 over square root of pi. Yeah? So we multiply and divide by square root of pi over 2 times the integral from 0 to 1 of e to the minus b squared dv. This now I of 1 is our original integral that we were looking for. Then we will factor the e pi over 2 1 minus 2 over the square root of pi integral from 0 to 1 of e to the minus b squared dv. This here is the definition of the error function, complementary error function, complementary error function evaluated in 1. So this is finally e pi over 2 complementary error function of 1. And this is the answer. Yeah, another Fromage integral. Okay, I hope you like it, and see you.